All right. Well, thank you everybody for coming out on this cold Chicago day, February 20th, to listen to this talk on enhancing semi-supervised learning. As you know, our group tries to hold a series of regular talks and events to inform and learn and collaborate as PyData community members. And we are so happy to introduce yet another fascinating talk here from a PhD student in applied mathematics at Illinois Institute of Technology.
Thank you all for being here.
And I don't want to mispronounce your name because I'm bad at
Oh,
this.
yeah.
I'm
Jean-Marie Kang. Okay.
Jean-Marie Kang.
Yeah.
Thank you very much for coming, and let's give him a round of applause. Okay, so let's get to this work. Take it away. Thank you so much.
Thank you. Thank you all for being here tonight to listen to this talk. And I just prepared for a LaTeX slide, so it's not a PPT, and I hope that's working well.
Still check it for you. Yeah, just to make sure. Now the screen is being shared.
So my topic today is enhancing semi-supervised learning via representative and diverse subdata selection. And here, subdata refers to a subset of data. So why is data annotation of high quality important? You can see that recently those AI like ChatGPT and Gemini and Claude and Grok and DeepSeek, they are all competing each other, and the annotated data with high quality is one of the most important aspects for training those kind of models. So the high quality annotated data improves model accuracy, generalization, and efficiency, and the speed of training, especially fine-tuning. So that leads to the next problem. So, but most real-world data sets are unlabeled, like patient data, like images from public resources and text data. They need manual and often labor-intensive labeling process. And next, we got budget challenges in data annotation. It can be quite expensive due to the time, effort, and expertise needed. For example, those patient data, they can only be labeled by like medical scientists, doctors, and so on. Only those people can label those data well. And you can see that AI company pay a lot of money for labeling, and Meta's Llama 3 model require 10 million human annotations during training, and the new Sense data set costs approximately $100,000. So our problem today is to do machine learning tasks on the low budget, and to address this problem, we often have three paradigms for this problem. So the first one is semi-supervised learning. It utilizes a small amount of label data combined with a large amount of unlabeled data to train the models. And here, the large amount of unlabeled data are for like studying or learning the structure of the underlying distribution of the data. And the second one is active learning, actively selecting the most informative data points to be labeled. Here, actively refers to that when you are selecting the data points and you consistently receive the feedback from the model, like you select 10 points and train and get the feedback and select another 10 points. And the third one is semi-supervised active learning. It's a hybrid approach that combines the strengths of both semi-supervised learning and active learning. So the previous study focusing on how to select data for labeling to enhance the performance of the trained model includes unsupervised selective labeling, uncertainty sampling, core set approach, kernel herding, and statistical subsampling. And kernel herding and the core set approach is the two methods that inspire my study here. Essentially, those previous studies that focusing on selecting there can be some mistakes on grammar. Those previous study focuses on selecting a subset of informative data. And here, to measure informativeness, we usually use representativeness and diversity to measure the informativeness. Representativeness is to ensure that the selected subset of data or subdata distributes similarly with the entire data set. And diversity is designed to select enough points from low density area for training models. Here, the low density, the principle of selecting diverse data points is beneficial for cluster assumption in semi-supervised learning, which is the H points are often lied in the low density area, just shown in this picture. You can see that those H points, which are essentially, very important for is training the SVM, are often lied in the low density area. So it's a two-dimensional Gaussian mixture model classification. So that's illustrates this principle. So what are the challenges in previous studies? The first three methods here, it should be two. I delete something just before it. I compile this LaTeX slide. With SOTA performance on certain dataset lack theoretical basis to substantiate their effectiveness, and their criteria are rather intuitive than theoretically induced. So it means that, yeah, it performs well, but it lacks theoretical basis. So we don't know if it works well on like other data sets that are not regularly used. And the last three methods with solid theoretical guarantees only focus on either representativeness or diversity. So they can't take care of both of representativeness and diversity. And there's another weakness of those methods with theoretical guarantee is that they need strong theoretical guarantee, which is not satisfied in real applications. Sometimes we call that fake assumptions. So why are we saying that representativeness plus diversity is better? You can see that the first one selects only representative data. So it select only certain type of the docs, let's say doc. And the second one, yeah, it select diversified data, but it selects too many outliers. Like this is a emoji, and this is a tiger dog, and I don't know how to call it. So our methods select the alpha MD one refers to a measure that select that measures both representativeness and diversity. So you can see that it selects age points and those representative points. So that's the difference. So this is our contribution. We are designing a process for selecting data from unlabeled pool to label. And it's model free, it's fast and efficient. It's the optimization with finite sample error bound and low computational cost, which is also efficient. And its generalizability is guaranteed by generalization bound under certain assumptions, which is actually reproducing kernel Hilbert space assumption. It's very mild in a field of kernel embedding. And SOTA sampling method, it's a SOTA sampling method in two popular semi-supervised learning frameworks, which are flex match and pre-match. And it outperforms active learning related method in supervised learning frameworks. Some of you may ask that why we are not adapting this method in active learning. It's because active learning has weak performance when the sample size is extremely low. Remember, we are dealing with low budget learning problems, and it needs dynamic alpha, which is determined by model feedback. While our method RDSS has a fixed alpha, like you will see what alpha refers to. So it's kind of like a hyperparameter that to be tuned. So our method fixes the hyperparameter before the subdata selection process. So here is the problem set up. Those notations are kind of hard to read, but you just remember that XN refers to the full unlabeled data set, and IM refers to an index set that contain, and XIM refers to the selected subdata. And our goal is to find a subset of data that is representative and diverse to XN. The basic idea is to solving the following optimization problem. So it's to maximizing the representativeness with a regularizer of diversity. And our lambda here is the like the coefficient for the regularization regularizer that balances the trade-off between the representativeness and diversity. It's very common if you study regularization, like I say lasso regression and anything regularized. So it's a very natural idea. And the fundamental setting is the first one is low budget, and the second one is sampling without replacement. Remember, we are doing sampling, and if we are doing sampling with replacement, it would definitely destroy the representativeness of the data, the subdata. So, and it also benefits bias and the variance reduction and precision increase. Yeah. And here we set M over over n less than 0.2 for experiments in the experiments section, and n much smaller than n in theoretical analysis under this fundamental section. So remember, we are trying to find a representativeness measure and a diversity measure in the following. So it reminds us of a method called kernel herding, which iteratively selects representative samples from a distribution to approximate its mean embedding in a RKHS. So it's a functional space. So you can see that it's just calculating the minimum of this function and select it's the argument that minimizes it, and then include that into the index sets of subdata and do that for n iterations. So it's a iterative method, and the complexity will be polynomial. So it's OMN. M is the size of subdata and N is size of full data. And essentially, this method is equivalent to minimizing the maximum mean discrepancy, which it's defined by this one. So it looks very ugly. But take a look at this. It's essentially measuring the mean of fx or the mean of fx of the subdata, and the mean of fx where x are from the full data set. So it's measuring the distance of the two functions in this functional space H, and to minimize its supremes, which is usually in practical problem, we call that maximum. So it's indeed a distance between those 2 point sets, and it's kind of like measuring the distance not in the Euclidean space, but in a functional space. So that's the difference, and it can avoid some like when you are only working in the space Euclidean space, when the data structure is like non-linear, has some manifold structure, then those kind of linear methods will expire. So it's very useful to do those kind of thing in functional space. And this stuff quantifies the representativeness of XIM to XM. So we are using the MMD for quantifying the representativeness, and observe that here, this term actually evaluates the similarity between each point. So when this K refers to a kernel function, which is here, which measures the similarity between any 2 points and the average similarity. So this one is actually the average similarity. So you can see that another benefit for using this concept is that it's a linear combination between this one is a constant because those xi, xj are selected from the whole data set, and this one is for the diversity, and this one is for like counter diversity. And combining them linearly, we get a criteria for measuring the representativeness. So if we want to increase the diversity, we may just use this term and replace those rep function by MMD and SK. Then we get like optimizable objective. That looks very simple, right? That looks like a very simple idea. It's naive, but it has strong power. If we set lambda to be 1 minus alpha over alpha m, the objective function can be rewritten by this. So, and it may remind you of the definition of maximum mean discrepancy, which is here. So the only difference is that here is from it uses alpha to replace 1. So it's kind of like a weighted average, right? And that defines a new concept called alpha MMD, denoted by this one, MMD square K alpha something. And that still looks ugly. But this one is very powerful because this MMD stuff, when we are using its weighted form, which is like putting weights to each K, K, Ki, Kj, Kxi, Xj, putting weights to all of them. And the weighted form it's a function with respect to the weights, and it's convex as a function of the weight. So it's not listed here because I don't think I got so much time for extending its proof technique, but I can tell you here in brief that those convexity can be exploited by the following algorithm called Frank-Wolf algorithm. So this algorithm only works for convex function. It may generally it can be applied to non-convex function, but for convex function, it achieves a great convergence. So use this algorithm, we can calculate the iterating formula given by this equation 7, and its only difference between kernel herding it's not P here, it's alpha P here. So you can see that it's still very simple, but then in the theoretical analysis part and the experiments part, you will see its power. So as an extension, this algorithm is called generalized kernel herding, which is very natural. But generalized kernel herding can select repeated samples that contradict the setting of sampling without replacement. Take a look at here. It selects points from the full data set. So the index sets of from 1 to n in each iteration. So it may select repeated samples, and that's not what we want. So what are we doing? What we are doing is it's adding a backslash IP star here, so that the selected subdata are excluded from the selecting pool. So that the idea is also very basic, and it's called generalized kernel herding without replacement, and it's employed as a sampling algorithm for this this method. Well, when you are writing AI papers, you must name your method with like cool name. So we are demonstrating our method on a Gaussian mixture model, but I think the it's not working well under projection. But hopefully you can see it clearly. So if you can see clearly, then you can see that only k-means and our method achieves like space filling properties. So it's like the points are filling this space, and it's not like gathering together or separate, go separate, or like randomly distributed. So that's a great demonstration of the power of our method. And so why do we use RDSS rather than k-means? You will see in the experiment part, because k-means has its computational complexity has a t parameter which refers to the iteration time. So it's running slow. It's running slowly, yes. So here is a theoretical analysis. It's not so important in this talk, because I think the PyData Association cares more about its application. So, but I will mention it to briefly why it's working so well. So here is the core set approach. It decomposes the generalized risk, which is the average risk over the underlying distribution of the data sets. It's unknown. And it can be decomposed by this one. It's very natural if you know how to. Okay. Mathematics is filled with decompositions. So this one is the empirical risk, which is like the loss function, the average of the loss function over the data set S. And so this one is called the core set. And this is unknown, but we can optimize it when we are training. And this one, it's called it can be bounded by something called generalization bound, and it's like not optimizable. But this one is optimizable. It's called the core set loss, the third term, and we derived a bound for this core set loss, which it's only determined by alpha MMD. Those K alpha, KC are all constants. So if we minimize the alpha MMD, we can achieve a lower upper bound for not lower upper bound. It should be smaller upper bound for RH. So this is the generalization bound, and it's very concerned in learning theory community. And another one is finite sample error bound. So it illustrates that this algorithm indeed minimize that alpha MMD, and with the decreasing rates of an O log M over M, which is not so good, but it works. It illustrates that this method works well. And the constant exists here is because when an when XIM star is identical to XN, this stuff won't be zero because there is a diversity term in it. So it won't be 0. So there's a constant in the upper bound in the right hand side. And so these are the two main theory for the algorithm. And now we are coming to how to choose the kernels and also the parameter hyperparameter alpha. So we need positive defined kernels to guarantee those theoretical properties. What is a positive defined kernel is like if you calculate the kernel with a matrix of k, xi, xj, then the matrix must be positive defined. That's the meaning of positive defined kernel. It has a more formal definition, but it should be written on the whiteboard. So the most common kernel is called Gaussian kernel, or sometimes RBF function. So it's similar to the Gaussian distribution function. And the sigma here is not called the variance, it's called the bandwidth parameter. And it's selected as the median of the distance of all the points. Why we are selecting median as the choice of the bandwidth parameter is because median it's robust. It's more robust than mean. And so that it won't be affected by like extreme valued points in a data set. So it's robust. And for tuning the alpha, we spent a long time to figure it out, but finally we found that by straightforward deduction, we have this bound. So it's like we are working on bounds, on fake assumptions, but it works well. It's upper bound the MMD between the subdata and the full data set on the low budget setting. Why we are doing that? Because we want to bound alpha MMD, and in the meantime bound the MMD so that it stays representative. It should be always representative because we cannot. Our goal is to achieve representativeness and diversity. And if like yeah, so we can just set alpha to lie in this interval, so that convergence rate of M and Z would not be larger than one of alpha M and D. So it's because that this factor is m over log m squared, and if we set alpha to be like 1 minus 1 over square root alpha m, then it's at most O square root 1 over m. Yeah. So that's the reason why we are doing this. It's not so good. We all know that it's not so good, but in the future, we will figure out how to define alpha. That's how to choose alpha, which that is dependent to the structure of the model and the structure of the data distribution. So you can see that our experiment, see the performance of our method in Cipher 10, Cipher 100, SVHN, and STL10. It's almost like, except for stratified sampling, it's the best one. But we remember that for stratified sampling, you should know the label of each data point so that you can do stratified sampling. And that's not like not realistic in real applications. So usually we don't refer to the performance of stratified sample. It's like knowing in advance, and it's unfair. And it's also this one compares the RDSS with other sampling points in this graphic, and it also compares with different active learning and semi-supervised active learning approaches and the supervised learning paradigm, because this method is not designed for dynamic process. So you can see that our approach still it works well, and like SOTA. And it, mainly in these two frameworks, the flex match and free match. And here, we studied the effect of different alpha, and we finally we found that the criterion derived by the last bound 1 minus 1 over square root m, it's the best one over like fixed alpha. It's kind of unfair to compare with fixed alpha over different budget, but we don't have any better like benchmark for comparing the effects of our choice of alpha. And you can here is the computation complexity, and this is a very concerned issue in practical problems. So it's it's sampling 400 samples from Cypher 100 dataset. So you can see that yes, the random and stratified sampling, they don't need so much time, but they do not work well. Usually we do not use random or stratified sampling if we want to enhance the quality, sampling quality. And what those three methods, for USL and active fine-tuning, it's in the references. There are two previous study on this problem. And you can see that there is a T in the time complexity term. So T refers to the iteration time, and it may vary. So if let's say if the subset size or the full data size increases, the T may change, and it's definitely worse than OMN, which is ours. And there's a direct comparison with active learning and semi-supervised active learning. And you can see that the orange one and the red one are ours. So it's prior to other methods, even if in active learning approaches. But it's not actually fits the active learning paradigm because it's not designed for that. We just compare them. So for the last part, what is the potential application of RDSS and alpha MMD? The first one is what I've been doing, but we meet some obstacles, and hopefully we'll conquer that. So it's optimal subsampling, which is a very theoretical problem with control of representativeness, and it's not issue in engineering, but selective labeling for LLM training is, I think, is a very important issue, and also scenario reduction for designing energy system. And these two application is what I've been collaborating with my fellows. So especially for the second one, it's very popular because like you can get a lot of text data, image data, but if you want to label them, you need to find a company like Scale AI and pay a lot of money for them. So you want to like reduce the budget for labeling and pay for the GPU instead. And obviously, our method has limitation because the assignment of alpha is independent of the structure of the distribution of data and the model. Well, it's only like alpha equals to 1 minus 1 over square root n. It's definitely not the best one. If we can find a distribution and model dependent strategy for alpha, our method can be more robust and it may be adapted in active learning diagram paradigms. And also it needs weaker assumption for generalization because sometimes data may not satisfy those kind of RKHS assumption, which is not mentioned here, but it's mild, but we need weaker assumption for generalization in more scenarios. So this is my talk today. Thank you all.
Thank you for that very interesting presentation. I wanted to ask you a little bit more about your discovery of this alpha parameter.